Hello everyone, my name is Vanio Rodrigues and I will present the work entitled Standalone Rate-Distortion FME Architecture. This work was developed in the Embedded Computing Laboratory at the Federal University of Santa Catarina, Florianópolis, Brazil. This is the agenda of my presentation. I will begin with the motivation of this work, then I will provide a quick background and comment on the most relevant related works. After, I will accept our architecture and discuss the reason behind our project decisions. I will then show the results of our work and compare to the baseline architecture. Finally, I will draw some conclusions of this work. Let's start with the introduction. Video is everywhere. We use it for entertainment, to connect with friends and family, and it can also be a valuable tool to work, especially in the days we're living in. According to Cisco, in 2017, 75% of the total internet traffic was video, estimated to reach 82% by 2022, and that was before the COVID-19 pandemic. Video-related consumption market is an ever-growing industry, worth billions if not trillions of dollars. Higher resolution displays that enhance the user experience are currently being pushed by the tech companies, which are trying to get a share of this market. Here we have the stats from a high-definition video available at YouTube, which has 30 frames per second and 24 bits per pixel. Calculating its raw size, we can observe that to be able to stream the video, it will require a bitrate of over 600 megabits per second, which is more than 10 times my current connection speed of around 6 megabits per second. If the video had a length of 90 minutes, you would be required over 400 gigabytes to store it, so good luck with that, YouTube. Obviously, this is not the size of the video at the YouTube servers. The video is compressed using a coding standard, which makes it possible to store and share the videos across multiple platforms. And this process is happening right now. The presentation was recorded with my laptop, which has an encoder inside that is receiving the raw frames of my presentation while it's being recorded, and processing it by exploring the tools of a video coding standard. By doing so, generating a bitstream according to that particular standard. The bitstream is then sent through a channel, such as YouTube or Dropbox, to your devices. And they have a decoder that reconstructs the video from the bitstream. Let's take a closer look at some of the stages of the video coding process. Each frame of the video will be divided into small portions called original blocks. The blocks will go through a prediction unit where the encoder will use the tools of this standard to analyze blocks previously encoded to find a reference block. This reference block is the closest to the original block, and that minimizes the residue, which is the difference between the original block and the reference block. The coding process has further steps, but we won't go into detail since our work is inserted inside the prediction unit. Taking a closer look at the prediction unit is split into two processes, interframe prediction and intraframe prediction. Each process is search for a reference block that minimizes the residue using different techniques. Interframe, which is where our proposed architecture is inserted, explores temporal redundancies by searching reference blocks of different frames, while intraframe explores spatial redundancies by searching a reference block of the same frame as the original block. After both processes are finished, the best reference block is chosen by a mode decision step. Interframe prediction is also divided into two steps: integer motion estimation, or IME, and fractional motion estimation, FME. IME is an initial search, which seeks to find a reference block. FME is a refinement of this process. It realizes an interpolation that generates new candidate blocks with fractional motion vectors, and then a new search to see if any of these candidates are better than the ones initially chosen by IME. The fractional motion estimation alone is accountable for nearly 34% of the total encoding time of HM, which is HIVC reference model. Let's talk about the FME and some related works. Here we have integer samples of a block. Samples, in this case, is the value of luminance of each pixel. The interpolation uses these samples as an input of a filter to generate new samples. The coefficients of the filters changes according to the positions of the fractional samples. The fractional samples are named after the array of samples used for its interpolation. For example, horizontal samples are generated using a row of integer samples as inputs. Vertical samples are generated by interpolation a column of samples. Vertical samples can be separated into two types: the first order vertical samples, which have integer samples as inputs, and the second order, which have horizontal samples as inputs. As the second order needs their inputs to be previously interpolated, interpolating them is a two-step process. These are all the fractional positions supported by the luminance samples in HEVC. Now we are going to discuss related works and compare them to HM. In the FME implementation of HM, the number of candidates interpolated and searched is 16. It works for all block sizes supported by the standard. It is rate distortion aware, meaning each fractional position has a cost inherent to its position, and it's taken into account during the search. It also does the residue block calculation, and it has 16-bit precision and the interpolation filters input. Pastos docs propose an architecture that interpolates 24 candidates in a three-step process. This three-step process leads to a high architecture stall and therefore more repetitive operation and memory access. It features an 8x8 block size and it's not rate distortion aware. But it has transposition of the original and reference block, and that's used to provide a residue block in its output. Its interpolation filters have 16 bits, just as HM. I've also, on the other hand, proposed an architecture that interpolates and searches all 48 possible candidates, which with an 8x8 block size as well, in a single process, which leads to better memory access and data reuse. It's not rate distortion aware and does not provide a residue block. It only provides a motion vector and a metric cost, as you may observe in the image below of its top-level architecture. It utilizes 10 bits as inputs of filter interpolations, which means that horizontal samples are rounded from 16 to 10 bits before being used to interpolate the second-order samples. This causes an increase in bit error rate, which we will discuss later on. Seidel features a similar throughput with 48 candidates and 8x8 block size. However, it is rate distortion aware, but it does not have rate distortion computation, which means that the rate term needs to be calculated by some external module that may lead to synchronization problems, since each term needs to be ready at very precise clock cycles. This architecture generates the residue block as one of the outputs and also the motion vector of the best candidate and the metric of it. The interpolation filters also have 10-bit input precision. The proposed architecture here takes Seidel as the baseline to build a fractional motion estimation architecture that keeps the same grid features such as 48 candidates and 8x8 block size. We modified it to implement features such as the rate term computation hardware and the 16 bits input at the interpolation filter. We also made some optimizations to the overall structure of some modules within the architecture, as we will explore in the following session. So to summarize, our work is developed into three main novelties, which are energy efficiency improvements, achieved by modules more energy efficiency when compared to the baseline architecture, some rate distortion enhancement by computing internally the rate term, and also an investigation in the impacts on quality, energy, and area of 16 bits against 10 bits at the interpolation unit. This is the interpolation data path of the baseline architecture. Taking a look inside one of the features module, we can observe 7 arithmetic operations. However, some signal inverting operations could be promptly within the next step, making them discardable, which then leads to a new 4 arithmetic operations module. Now taking a look inside the transpose buffers. Originally, the output was connected only to one row, so the switching activity was very high during output reads, since all the data needs to move to that row to be read. This is our proposed transpose buffer. All the rows are connected to a multiplexer, so that each row can be randomly accessed, thus eliminating all switching activity from the buffers during data reading. This is the search data path of the baseline architecture. Our third energy improvement is on the candidate and best buffer. Baseline architecture implemented them as first in, first out buffers. And so register cells are being written every clock cycle, leading to high dynamic power dissipation, which changed. So buffers now work similarly to an SRAM, and so any row can randomly be accessed for both reading or writing. By doing so, eliminating most of its switching activity, since only one row is active per clock cycle. Now to rate term distortion improvements. The rate term is shown in equation 1, and it is implemented by the left data path, which generates a unique rate term for each of the 48 candidates, which then summed with the distortion cost. The Golomb term, shown in equation 2, is implemented by the right data path, and it is used by the rate term data path. Now we will discuss the results. The experiment setup was as it follows. The proposed architecture was synthesized using Synopsys Design Compiler tool in topographical mode. All synthesis used the 45nm TSMC standard cells library. We used the default switching activity for power estimation. The input and output delays were limited to 6% of the clock period. Finally, the design compiler was restricted to keep the RTL hierarchy during the synthesis to obtain detailed area and power reports. These are the results of the coding efficiency gain by computing 48 candidates with 16 bits interpolation input instead of 10. We may observe that the coding gain is very small over all classes, with averages of 0.03% bit rate gain. This table shows the power results of our architecture and their percentage increase compared to the baseline architecture for 3 target throughputs. You obtain an average of 28.6% area increase and 33.7% in total power increase. Now looking at the percentage power variation of each module when compared to the baseline project, you observe that horizontal transpose buffer and the features module have an increase of 48 and 75%, and that is due to the use of 16-bit samples that are now stored and interpolated in them, while interpolation transpose buffers show a decrease of minus 13% due to the changes in the TB organization shown before. Same as for the candidates and the original transpose buffers. The others modules had an increase due to the rate distortion implementation and some bigger register barriers to support the 16 bits. And here we have an area and power breakdown. Area is on the left and the power is on the right. We notice that the horizontal transpose buffer HTB is responsible for the biggest share, and that's why the 16 bits modification has such a bad impact in the power results that we seen before. The rate term data path accounts for only 4% of total area increase and 2.3% of the total power dissipation. Now for the conclusions of our work. We presented an FME architecture with improved encoding efficiency. Our design ensures that no routing error occurs in interpolation of the fractional samples by using a 16-bit input at filters. We also achieved a bit rate gain of 0.03%. It also ensures that the optimal candidate block is selected by internally computing the rate term. While our proposed architecture was designed to work with 8x8 blocks, it can easily be extended for other block sizes. We also improved the energy efficiency by creating individual designs for each buffer, which leads to less switching activity for both reading and writing. We also observed that the horizontal transpose buffer is the most resource-consuming component of our architecture, so changes to its design will have big impacts on the overall results. When compared to the baseline architecture, our design had an increase of 28% in area and 33% in power. We plan on conducting a more precise power estimation methodology with real input values for encoded sequences. We speculate that the proposed buffers will perform a lot better against the baseline architecture with a more realistic switching activity. Well, thank you all for your time. If you have any questions, please feel free to send me or any of the co-authors an email, and we will be pleased to answer it. Thank you so very much.